Hello everybody, welcome back to another video, and in this video we'll be looking at types of nested root integral questions. So what do I mean by this? Well, we can see the first example here. In this first example we have the sums of the square roots of x, and that is going to be happening an infinite number of times. So we have the square root of x plus the square root of x, and that will go on for infinite number of times as mentioned. So how do we deal with this? Well, what we often do is we see that we have some function y, of course, being equal to what we're integrating here, so it's the infinite square roots. And what we'll often try to do is we'll have to try to reduce this into something that is finite, or something that we can deal with more easily than this. So what we see is that this is happening in infinite number of times. And a key idea that we have to see here is that infinity is the same as infinity, regardless whether it is infinity minus 1 or anything else. So what we see here is that this entire expression right here is going on an infinite number of times. And then what we also notice is that we have the square root of x plus, and the same operation is being repeated. So that means that this expression right here is also happening an infinite number of times. And so is this expression. And by definition, y is the infinite nested square roots. So therefore, what we see is that this part right here is also y. So what we can see is we can reduce this to see that y is just the square root of x plus y. And what we can do here is we can solve for x. So we square both sides. We see that y squared is x plus y. Subtracting the both terms on both sides, we get y squared minus y minus x is equal to 0. And what we see is we have a quadratic in terms of y, because x here is the constant. And of course, we look at the coefficients of y. So 1 times y squared and minus 1 times y. So here, of course, we can use a quadratic formula. So we take minus b minus minus 1. So 1 plus or minus, and that is something I'll touch on later, the square root of b squared, which is minus 1 squared, 1, minus, and what we see is we are subtracting 4 times ac, which is 4 times 1 times negative x. So that 4 times negative x, which is negative 4x, and subtracting negative 4x, that will become a positive. So we add 4x, and that is all divided by 2a, and 2 times a is 2. So what we have here is we have this expression. We have y is going to be equal to this. So what do we see here? Well, we have two expressions here. We have a positive and a negative root. So which one should we take? Well, the first thing we notice is that x must be greater than 0, because if x was negative, we would be dealing with complex numbers here. And we know that our original integral is in the real world, and there's nothing complex here. And if x is greater than 0, that means y is also greater than 0. So what we can immediately see here is that we cannot take the negative root, because if we were to have some negative number, let's say something that would produce a perfect square, like x to be, take x to be 6, then 4 times 6 is 24, 1 plus 24 is 25, square root of 25 is 5. And if we take 1 minus 5, that's minus 4 over 2, that's minus 2. We see that y is minus 2, and that is not possible, because we know that our integral is in the real world only. So it would make sense to see that y is greater than 0, which then implies that x is greater than 0. So what we see here is that we have to take the positive root. And now what we're really integrating is we're just integrating this function of y, because originally what we are doing is we are just integrating this and integrating this. And now what we're doing is we're doing the exact same thing. We integrate y, so we integrate this, because we have just found an equivalent expression in terms of x in terms of y. So we're integrating 1 plus, and then what we see, we have everything over 2, so we can take that 1/2 constant out. We're integrating 1 plus the square root of 1 plus 4x. This is a pretty standard integral here, so we see that this is now 1/2 times integral of 1 is x, and the integral of the square root of 1 plus 4x, we do a simple u sub here, so we see that this, we take u to be 1 plus 4x, therefore du is 4 dx, and dx is du by 4. So what we have here is we are just integrating, so let's just put this here. We have to add now the integral, and we have the square root of u, because our u is 1 plus 4x, so u to the 1/2 power, that's the same as the square root of x. And of course, we have du by 4. So what we have is we can just take this 1/4 constant out, and what we have here is now 1/2 x plus 1/4, and then let's just evaluate this right here. We have u to the 1/2, so that becomes, add 1 to the power, so 1/2 plus 1, that's 3/2. Divide by 3/2, that's the same as multiplying by 2/3. So you have 2u to the 3/2 all over 3. And let's start simplifying some stuff here. We see that what do we see here? Well, this is actually this also has a 1/2 because this 1/2 was factored out of the entire integral. So what we see here is that this is also being multiplied by 1/2. So what we actually have here is we have 1/2 x plus 1/8 all times, and then let's replace our u back with 1 plus 4x. So 1 plus 4x to the 3 over 2 over 3. What we see is that we can cancel this out. It becomes 1/4. 1/4 times 1/3 is 1/12. So our final answer is 1/2 x plus 1/12 of, and then let's just put this on the numerator here. We have 1 plus 4x to the 3/2 power, and we can put a plus c. So this is our answer for this first nested integral problem. Now let's look at the second problem, which is a bit easier. So the second problem, we have the integral of the square root of x multiplied by the square root of x times the square root of x, and so on. We see that we are multiplying the square roots of x forever. So there's two ways we can approach this problem. We can use the similar approach to the thing that we did in the first integral. And let's try that first. So we see that we have y, our function y, to be x times the square root of x, and so on. Therefore, we also see that y is equal to the square root of x times y, because this infinite nested square root is going on for the infinite number of times, regardless if it is also inside this infinite nested square root. Infinity is still infinity, regardless of whether you're inside one iteration of the infinity. So what we can see now, we can square both sides. Y squared is equal to xy, and we can legitimately just divide both sides by y. And what we see here that is pretty cool is that y is just equal to x. So this entire expression here, the square root of x multiplied by the square root of x, it just evaluates to x. And that will be useful not just when integrating this, of course, but in other useful math settings. If you have a nested multiplication of square roots of x, that just evaluates to x. So what we're integrating here is this is the same thing as the integral of x dx. And of course, everybody's favorite integral question, this is just add 1 to the power, divide by the new power. That's x squared over 2 plus c. And another more intuitive way that we can look at this and see why this really does converge to just x is we can actually see, since these are being multiplied and since these are nested square roots, we can see each root as a fractional power. So the first thing we have is we have x to the 1/2 power. Now that's being multiplied, so let's just do this here. Let's just do it like this. So first thing we have here is we have x to the 1/2 power, and that accounts for this x in this square root. Now the next thing we have is we're multiplying it by another x. We have an x to the now, and then what we see here is that we have this x, which is in a square root, but that's also in another square root. So we have a square root of a square root, which is 1/2 times 1/2, so that's x to the 1/4 power. Now that's being multiplied by another x, and let's just say it's this, and that is going to be this x in another square root that's inside those square roots. So it's 1/2 times 1/4 once again. And what do you see? This is 1/8. And what we'll see is that this will continue going on, and we have just x to the 1 over 2 to the nth power. We have the reciprocals of the powers of 2. And of course, what we now can simplify this to is, because these are being multiplied and they have the same base, we can add the power. So this is the same thing as x to the 1/2 plus 1/4 plus 1/8 plus dot 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 plus 1 over 2 to the n. And of course, n here is going to infinity. And what do we see here? This is a very, very famous summation problem. This is just x to the sum of a geometric series where, let's say, n is starting at 1 here because we have 1 over 2 to the 1 to infinity of 1 over 2 to the n. And this is a very summation problem. This right here evaluates to just 1 because of, you can use the infinite geometric series formula, and you can also prove this visually and geometrically. But what you eventually see, this is just equal to x to the 1. So what we're doing is we're just integrating x to the first power dx. That's just going to be x squared over 2 plus c. So that is a cool way that you could look at it using an infinite geometric series, which is really what these infinite nested square roots are. And the final, I would say, most fun problem, and that is the integral of, and then let's see here, we have a giant radical. We have the integral of the square root of x. So let's just put a 2 here on purpose. This 2 represents a square root. It's the same thing. Then we have to multiply by the cube root of x, like so. then multiply by the fourth root of x, then multiplied by the fifth root of x. And we see where this is going. We are multiplying each time by 1 over n plus 1th power of x, as, of course, n goes to infinity, because this is an infinite radical. So you can put a dot, dot, dot here, and just put 3 dots. So this is, of course, the integral now. So what do we do here? Because we can't simply set this as a function of y and then try to simplify this into something of finite length, because this has changing radicals as we progress through each iteration of this entire giant radical. So what we need to do is we need to employ a similar method to the method that we took right here, which is to look at the roots as multiplications of different powers of x. So what we see here is that we have the square root of x. So let's write that like this. We have the square root of x. This is the first part. So this, let's just do that. And we have the square root of x. So we know that the first term is x to the 1/2 power, because square root is taking the second root, which is x to the 1/2 power. And I can make a note here that the nth root of x is x to the 1/n, like so. Just a simple index law. Now, let's look at the second term. The second term, we're multiplying by the cube root of x, like so. And normally, if we have the cube root of x, just like this, that's going to be equal to x to the 1/3 power. However, we are inside of a square root, and as the terms are being multiplied, you can look at this as x to the cube root of x inside of the square root of x. And that is really what this term is right here. And what is the cube root of x? That's x to the 1/3 power. And that's all in a square root. And what is a square root? That's raising that to the 1/2 power. So we have x to the 1/3 times 1/2 power as being our next thing. So what we see here is that we have to multiply now by x to the 1/3. I'm leaving it like this on purpose, times 1/2 power. Now our next term we see is the fourth root of x, like so. And what we see here is that this fourth root is inside the cube root and the square root. So we know that we have 1/3 times 1/2 for this term. This next term is inside of a fourth root, so we have to multiply by 1/4. So we now multiply by x to the power of 1 to 1/4 times 1/3 times 1/2. And what we'll see that we have a very, very nice pattern here, because what we see is that this operation right here on the denominator is just a factorial, because of course by definition a factorial is multiplying n by n minus 1 until you reach 1, but of course multiplying by 1 doesn't change the entire expression. So this right here is just the factorial, or more precisely the reciprocals of the factorials. So what we see here is that these are the same base, they're being multiplied, so this is equal to x to the 1/2, and then we add the powers, of course, 1/3 times 1/2, and then we add 1/4 times 1/3 times 1/2, and more precisely now we can write this finally as 1 over and then 2 factorial plus 1 over 3 factorial plus 1/4 factorial, and then we can guess the next term will be 1/5 factorial, and that checks out because we have the fifth root, and I forgot to put in x here, so this is the fifth root of x, and then multiplied by the sixth root of x, of course. So yeah, and here that is going to be 1/5 multiplied by all of the previous radicals here. So that is a key idea, that it's nested, so we have to multiply by each of the previous powers, like so. So then what we see here is that all we need to do is we need to evaluate x to the sum from this time n is equal to 2, because we see here, and of course to infinity, we're taking the reciprocals of the factorials, which is 1 over n factorial, and in order for our first term to be 2 factorial, n must start at 2, of course. So how do we evaluate this? Well, what we need to see is that this very closely resembles the Taylor series expansion for e to the x. So we know that e to the x, the Taylor series expansion is the sum from n is equal to 0 to infinity of x to the n over n factorial. And how do we get to this sum right here? We have 1 over n factorial, but we also know that as x is our input, we need to just find a value of x that when raised to the power of any number will remain to be 1. And of course that is 1, because 1 to the power of anything is 1. So we see to get this function part right here in this summation, x needs to be 1. So we see that here we have e, and that corresponds to e to the x, which is e to the first power now. The sum from n is equal to 0 to infinity of, and then we have 1 to the n, which is always going to be 1 in the real world, of course. And here we have 1 over n factorial. So we are almost done because we see that e to the first power, which is what corresponds to x to be 1, is just this summation right here. However, what we notice is that the starting value is different. We're starting from n is 0, and here we're starting from n is 2. So how do you figure that out? Well, let's see what this looks like. This right here, we can try plugging in the first thing. We know plugging in 0 into n, 0 factorial is 1. 1 over 1 is 1. So we have 1. Now, but I'll just write this as 1 over 1. Then we add now, and then plugging in 1 factorial is also 1. So we add 1 over 1. Then plugging in 2, when n is 2, 2 factorial, we have 1 over 2 factorial. So what we see here is, I'll even write it like this. And then, of course, the next term will add 1 over 3 factorial. And what we see here is that this summation right here corresponds to 1 over 2 factorial plus 1 over 3 factorial dot dot dot. And this is also a dot dot dot. What we see here is that this part right here is exactly what we have here. And what we see here is to get the equivalent expression, all we need to do is subtract these first two terms from our left-hand side, which is e to the first power. So we see that the sum, finally, from n is equal to 2 to infinity of 1 over n factorial is just equal to e to the first power minus the first two terms of this expansion when x is 1. So we see that's minus 1 over 0 factorial minus 1 over 1 factorial. And guess what? That corresponds to e to the first power minus 1 over 1 minus 1 over 1, which is minus 1 minus 1, which is minus 2. So e minus 2. So all we have here is just x to the e minus 2. So that is really, really cool. This entire expression converges to x to the e minus 2 power. So all we're left is the integral now of x to the e minus 2 power dx. And of course, e minus 2 is a constant, so we can just use the power rule, our favorite rule. So what do we see here? We add 1 to the power. So this is x to the e minus 2 plus 1 is e minus 1. Divide by the new power, e minus 1. And let's put a plus c because we are done now. So this was a really fun problem. And just to recap everything that we did there, we looked at the radicals as multiplications of their powers. And this is almost like a recursive formula because you're multiplying by the previous iteration power, which is the 1 over n minus 1th power of x, and we see that those are actually the reciprocals of the factorials. Then we notice that the Taylor series expansion for e to the x, when x is 1, corresponds to the sum of over the positive integers from n is equal to 0, of course, of the reciprocals of the factorials, and that corresponds to e to the first power. However, we see that we're starting from n is 2, so then we have to subtract the first two terms, and the first two terms sum to be 2, so we get e minus 2, so therefore we have x to the e minus 2, to be what all of this converges to, which is super duper cool. So then we're just integrating that, and we have a simple power rule. So that is it today's video, and thank you for watching.